In this video, we're going to look at the reverse of what we just looked at, which was product to sum. Now we're going to start with a sum and we're going to go to a product. And there's lots of reasons to do that, and we'll look at some examples. All right, so instead of deriving these identities, we're going to just list them out. Here is the first one. If you have the sum of the sine of an angle alpha plus the sine of an angle beta, that is going to equal 2 times the sine of the quantity in the numerator, alpha plus beta, all over 2, times the cosine of the quantity in the numerator, alpha minus beta, all over 2. All right, now, if instead of the sum, we have the difference, what changes? It looks like we still have 2 times the sine, but inside that sine, the argument, instead of having alpha plus beta like we saw before, now we have alpha minus beta all over 2. And the same thing is happening for cosine. The cosine turns into the quantity in the numerator, alpha plus beta, all over 2. Okay, so the only things that have changed here is when we had a plus, when we had a sum, we had a sum in the first factor and a difference in the second. When we started with a difference, then in the first factor, we still have a difference, and then we have a sum. In the class that I teach, I do not require students to memorize this. It's just an observation. Depends on what class you're coming from, whether or not you have to memorize or not, but just an important thing to point out in case you do want to memorize. The third one is the sum of the two cosines. So the cosine of alpha plus the cosine of beta is equal to 2 times the cosine of the quantity alpha plus beta in the numerator all over 2 times the cosine of the quantity alpha minus beta all over 2. For the difference of cosine, that's going to equal negative 2 times the sine of the quantity alpha plus beta in the numerator all over 2 times the sine of the quantity alpha minus beta all over 2. Let's take a look at an example now. Part A. Write the sine of 4 theta minus the sine of 6 theta as a product. Okay, so keeping in mind what our identities are, let me write this out. So I'm going to say that the sine of 4 theta minus the sine of 6 theta is equal to, so I'm looking for the identity that has a sine minus a sine, and that is the second one that's listed here. So that is going to equal 2 times the sine of, I'm going to subtract the two angles, so 4 theta minus 6 theta all over 2 times the cosine, and now I'm going to add the two angles, so 4 theta plus 6 theta, 4 theta plus 6 theta all over 2. Try to squeeze that all in there. Now let's simplify as much as we can. 4 theta minus 6 theta is negative 2 theta, and I can simplify by canceling out those 2's, and I'm left with negative theta as my argument, times the cosine of, let's see, 4 theta plus 6 theta is 10 theta, and 10 theta divided by 2 is 5 theta. And then the final step to do here, because we know sine is an odd function, that negative inside the argument of the sine function, we can pull that negative to the outside to have a final simplification as negative 2 times the sine of theta times the cosine of 5 theta. And I think that's as far as we can go. All right, part B. Now we have actual numbers. We have actual angle measures, so we should be able to do a little bit more with this one. So this one wants to, for us to take the sum of the cosine of 100 degrees plus the cosine of 200 degrees and write it as an exact product. Now, one thing that we know from our past work with identities is that this is not equal to the cosine of 300 degrees. I wish it worked that easily, but it just doesn't. You can put it into your calculator and see it just doesn't. So we have to rely on these identities. So let's go ahead and do that. The one that we're looking for is a cosine plus a cosine. All right, so I'm going to write the cosine of 100 degrees plus the cosine of 200 degrees. What does that equal? That equals 2 times the cosine of, now I think I'll go ahead and do this part in my head, or I'll just say it out loud. I'm going to take the two angles and add them together. So 100 degrees plus 200 degrees is 300 degrees, and 300 degrees divided by 2 is 150 degrees, isn't it? Times the cosine, now I'm going to subtract. So 100 degrees minus 200 degrees is negative 100 degrees, and negative 100 degrees divided by 2 is negative 50 degrees. All right, let's keep going. So I guess I could, I've got the cosine of a negative degree measure. So I know that cosine is an even function. So that means that the cosine of negative 50 degrees is the same thing as the cosine of positive 50 degrees. Okay, so that looks good. And what else can I do? 150 degrees is one of my special angles, isn't it? What is the cosine of 150 degrees? Can I simplify that a little bit? 150 degrees is over in the second quadrant, and the cosine is negative square root of 3 over 2. 50 degrees is not a special angle, so I'm just going to write this as the cosine of 50 degrees. And it looks like my 2, because that's 2 over 1, the 2 in the numerator and the 2 in the denominator can cancel out, right? That was 2 over 1. And so I am left with negative square root of 3 times the cosine of 50 degrees. Could I get an approximate answer by using my calculator? I could, but notice in the instructions this one wanted an exact product, and so that is it. Now let's use the identities to actually solve a problem. This example says to solve the equation, the cosine of 2 theta plus the cosine of 4 theta equals 0, over the interval where theta is between 0 and 2 pi. So what we're being asked to do is actually come up with the possible angles, the possible angle measures, that when I put those angle measures in, and in the first term times it by 2 and then take its cosine, and in the second term times it by 4 and take its cosine, add them, I get 0. All right? And because I have a sum here, I want my sum to product identities. And the reason I want to write this as a sum to a product has to do with something called the zero products property. The zero products property says that if you have two things that multiply and equal to 0, then either the first thing must equal 0 or the second thing must equal 0. See, for me to try and solve for theta right now, I cannot do a split and set, for example, the cosine of 2 theta equal to 0 and the cosine of 4 theta equal to 0. I can't do that. It doesn't work with the sum. It only works with the product. So if I can rewrite this sum of cosines as a product, then I think I'm in business. Let me show you what I mean. So I have a cosine plus a cosine. So I'm going to take this whole left-hand side and I'm going to rewrite it as 2 times the cosine of the quantity. It's alpha plus beta, so I'm going to have 2 theta plus 4 theta all over 2 times the cosine. Now I'm going to subtract, so it's going to be 2 theta minus 4 theta all over 2, and I'm going to set that equal to 0. Let me make this look a little bit better. I'm going to say 2 times the cosine of, let's see, 2 theta plus 4 theta is 6 theta. 6 theta divided by 2 is 3 theta. And then 2 theta minus 4 theta is negative 2 theta divided by 2 gives me negative theta. Of course, we know that negative theta, for the cosine, that's going to turn into a positive. But we'll deal with that in a second. Okay, so now we can start the solving process because we do have multiplication. So I'm going to set the first factor of 2 times the cosine of 3 theta. I'm going to set that equal to 0. I'm also going to set the second factor, the cosine of negative theta. I'm going to set that equal to 0. And I'm going to solve each one of these equations to come up with the angles that I'm interested in. All right, so let's start with this first equation. I'm going to eventually try and get this theta by itself. To begin, I'm going to divide both sides by 2. That gives me the cosine of 3 theta is equal to 0. Now, I want you to keep in mind that because the argument has a 3 in it, in other words, it has this b value of 3, that is changing the period of the function, isn't it? The period, or how often this thing repeats itself, is every 2 pi over 3 units. So we're going to have to remember that because we're looking for all of the solutions between 0 and 2 pi. All right, so I'm going to take cosine inverse of each side, and that's going to give me 3 theta equals cosine inverse of 0. So what angle produces a cosine of 0? So you need to have a good understanding of your circle. 3 theta is going to equal, I think that happens at pi over 2. That also happens at 3 pi over 2. So I'm going to say 3 theta equals 3 pi over 2. And if I divide both of those by 3, I get theta is equal to pi over 6. I get theta is equal to 3 pi over 6, which simplifies to pi over 2. All right, now those are great solutions. However, because of that period change, we're going to want to remember that if we can add multiples of 2 pi over 3 and we can get solutions that are within this 0 to 2 pi, then we have to consider those. All right, so we'll come back to that in a minute. Let's move on to the second equation. The second equation is the cosine of negative theta equals 0. So let me solve that. We know that the cosine is an even function, so I'm going to say that the cosine of theta is equal to 0. So theta is equal to the cosine inverse of 0. What angles produce a cosine of 0? Well, those angles are, I think we said this before, pi over 2 and also 3 pi over 2. Now, this particular equation didn't have a change in the b value, so those are the solutions. There's nothing beyond that. I guess what we could say is there's a plus 2 pi k here on the end, but we know that if we add 2 pi, that's going to take us over that that limitation that is in this problem. So let's move on to these the first equation that we dealt with. Okay, so if theta is equal to 0, then of course we know that pi over 6 is a solution. Let me just highlight that. So pi over 6 is a solution, pi over 2 is a solution. But what if k value is equal to 1? Well, if that's the case, then theta is also, let me get rid of that, then theta is also equal to pi over 6 plus 2 pi over 3. What is pi over 6 plus 2 pi over 3? Well, 2 pi over 3 is like 4 pi over 6, and 4 pi over 6 plus 1 pi over 6 is 5 pi over 6. I could do the same thing for the second part of this, so I could have pi over 2 plus 2 pi over 3. What is pi over 2 plus 2 pi over 3? Let you sort of think about that for a second. When I did that, I got a common denominator of 6, so I got 3 pi over 6 plus 4 pi over 6, which gave me 7 pi over 6. All right, so I've got two other solutions. Messed that up, didn't I? Let me erase that. I keep going to that wrong pen. So I have, what did I say this was? 5 pi over 6? 5 pi over 6? I just want to highlight it. So 5 pi over 6, there it is, and 7 pi over 6. Those are also solutions. Do you think I can squeeze anything else in? Well, I'm running out of room, but let me just move over here to the side. And I'm going to say, if I take 5 pi over 6 and I add another 2 pi over 3 to it, what do I get? Can I squeeze something in? Well, let's see. 2 pi over 3 is 4 pi over 6. 4 pi over 6 plus 5 pi over 6 is 9 pi over 6, which is 3 pi over 2. Great, that works, but we already have that one, don't we? We already had that one, and maybe I should highlight it, huh? We already had that solution here, and we here had it there. All right, so yes, it is true, but it's redundant, right? So I don't need it. If I add another 2 pi over 3 to that, I think I get too big. I'll let you check that on your own. Actually, no, I'll just do it here. Let's see here. 3 pi over 2 plus 2 pi over 3. That's like, let me see, my common denominator would be 6. So I'd have 9 pi plus 4 pi. So that would be 13 pi over 6. Yeah, that's too big. Too big. Too big. All right, what about that 7 pi over 6, though? 7 pi over 6, if I add 2 pi over 3 to that, how's that work? 7 pi over 6 plus 4 pi over 6 would be 11 pi over 6. Yep, I think that will work, won't it? All right, so let me highlight that. And I just noticed that I highlighted the pi over 2, didn't I? Highlighted pi over 2 here, and we already had it here. So that's also a redundant one. And so maybe I'll just cancel that one out. Okay, if I add 11 pi over 6 is almost 2 pi. I can see that if I add anything else to that, it's just not going to fit. It's not going to be within that 0 to 2 pi space or limitation. So I wish I had more room. I really do. But I don't, so I'll make the best of it. I'm going to say that the solution set, because this one said to solve, you always want to write your final answer as a solution set. I'm going to say that that solution set is pi over 6, right? That was the first one I found. And if I put these in order, I think the next one would be pi over 2. And then, let's see, so I took care of that. And then 5 pi over 6, 5 pi over 6. And then 7 pi over 6. And let's see what else. 3 pi over 2. And finally 11 pi over 6. So we have, what, 6 solutions, which sort of makes sense when you think about that 3 in there, right? What's it doing to the period? We're seeing it repeat 3 times as often. So normally we have 2 solutions. So it's almost like you're multiplying by 3 to get 6 solutions. So the final answer, if I had room, the very last line that you would write would be that solution set that I've highlighted for you. So this solution set right here that I just said out loud. All right, let's try one more where we are being asked to verify an identity. And we're being asked to identify an identity where it may be helpful to rewrite using the sum or difference identities. So this one says to verify the identity that in the numerator that the cosine of the quantity 4 theta minus the cosine of the quantity 2 theta all over the sine of the quantity 4 theta plus the sine of the quantity 2 theta, that is equal to negative tangent of theta. Certainly writing negative tangent of theta on the right is much nicer than what we see on the left. So let's see if we can actually do that. So up in the numerator we have a cosine minus a cosine, and so I'm going to use my identity that deals with cosines minus cosines. So I'm going to rewrite, I'm going to use that highlighter again, I'm going to rewrite this numerator. All right, I'm going to rewrite that numerator. So cosine of 4 theta minus the cosine of 2 theta is going to be, make sure I've got enough room, it's going to be negative 2 times the sine of the two angles added, so 4 theta plus 2 theta all over 2 times the sine. Now I'm going to subtract those angles, so 4 theta minus 2 theta all over 2. That is my numerator, and I'm going to put that over equals, I'm going to put that over the denominator. I'm going to try and simplify this denominator. In this denominator, I have a sine plus a sine. So I'm going to use, let me get my pen out. I'm going to use the sine of an angle plus the sine of an angle. So that's going to equal 2 times the sine. I'm going to add those angles and divide by 2. And then I'm going to take the cosine of, I'm going to subtract those angles and divide by 2 and hope that this all works out. So now I've got some simplifying to do, don't I? So let's see. Up in the numerator, I have -2 times the sine. 4 theta plus 2 theta is 6 theta. 6 theta divided by 2 is 3 theta times the sine of 4 theta minus 2 theta is 2 theta. 2 theta divided by 2 is just theta. That looks way better. And okay, so that came from my numerator. Now I'm going to work with the denominator. So I'm going to get 2 times the sine. We already said 4 theta plus 2 theta all over 2 is 3 theta. And same thing with this cosine. 4 theta minus 2 theta is 2 theta divided by 2 is theta. Okay, so now I'm hoping some things simplify, and I see some things that will simplify, which will make it real nice. We have one of our factors is the sine of 3 theta. We have that not only in the numerator, but we also have that in the denominator. So I can cancel that whole thing out. And then -2 divided by +2, right, becomes -1. So let's see here. I have -1 times the sine of theta over the cosine of theta. Well, we know that the sine over the cosine is equal to the tangent, don't we? That's one of our reciprocal identities. And then we'll just hook that negative on, and I think you'll see that we have turned the left-hand side into the right-hand side, and thus we have verified this identity.